Whether you are here with us at the NSF NCAR Mesa Lab or joining us virtually, thank you for sharing your time with us today at this NSF NCAR Explorer Series lecture titled Keeping Space Safe, Understanding the Impacts of Space Weather on Satellite Orbits. I am Elizabeth Mays and part of the Education, Engagement, and Early Career Development, or EDC team that shares NSF NCAR's world-class research through the Explorer Series. The U.S. National Science Foundation National Center for Atmospheric Research, or NSF NCAR, is a world-leading organization dedicated to understanding Earth system science, including atmosphere, weather, the sun, and the importance of all these systems in building national resilience and protecting communities. And with that, I would like to formally introduce our speaker. Dr. Nick Pedatella is a scientist in the High Altitude Observatory, or HAO, at NSF NCAR. And his primary research interest is in the variability and predictability of the mesosphere, thermosphere, and ionosphere, with a particular focus on the coupling of these regions with terrestrial weather. So now, before I turn it over to Nick, let's go ahead and check out what our thoughts are on the word cloud. All right, so we have magnetism, fast, solar flares, hard, in parentheses, light, small, slow, solar flare, hailing, and big. So a lot of description words there. So with that, I'm going to hand it over to Nick to continue with the lecture.
Thank you, and thanks everyone for choosing to spend your Wednesday evening here for the lecture. So I'm Nick Pedatella. I'm a scientist here at NSF NCAR, working mostly, as was said, on modeling and predicting the space environment. And so what I'll focus on today in the talk is mostly the impact that space weather can have, focusing mostly on satellite orbit prediction and its effects on the space environment, with some brief diversions into kind of other areas where space weather can impact technology. So I'm going to start with a movie here, which is showing the sort of almost current environment around Earth. And this is looking at all the objects that we can track in the space environment. This is 2 years ago, so now it's even more. You'll see in a few slides how much more is there now. But as of about 2 years ago, this is what the space environment looked like, and I'll play it again. And so you can see here, close to Earth, there's all this stuff kind of moving around very fast, and it's a very congested environment. And then further out, you see this kind of ring, and that's more the geostationary satellites where they stay kind of fixed over one place of the Earth. But with all of this stuff up there, that is kind of where our concern is and what we want to understand, the effects on this environment and how it impacts all of this operations of satellites and things like that in this environment. And of course, it wasn't always so crowded. Here's a political cartoon saying that 50 years when I was in space, there was actually space, and the implication being, well, now it's no longer space. It's sort of full of other things, and so it's no longer quite as pristine of an environment. And if we look at how this is changing over time, 50 years ago, it was really almost empty, you could say. So this is a time series looking at all the objects that we can track in space. So this isn't everything. This is only really objects about bigger than 10 centimeters in size. So there's still a population that we know is there that's smaller, but is not on this. And so if you look at the total number now in kind of current day, it's around 40,000 objects. But really, 50 years ago or so, it was much smaller, and you can see it's kind of rapidly increasing with time, especially in the last few years with sort of increasing commercial constellations. And this is kind of different types of objects that are in space. There's active satellites, which is what we often think of as filling up the space environment, things that are still being used and contributing to communications, navigation, things like that. There's sort of fragmentation debris which is one of the concerns that we'll get into more in this talk, and that's essentially from collisions between two objects. And you can see there's kind of jumps in this time where a few times you get a kind of rapid increase in the amount of this fragmentation debris, and that's the result of a collision between two objects that occurred at that time. And then there's other kind of almost you could think of as waste to some degree. So when you launch something into space, there is some leftover debris from the rocket body or launch vehicle that is often left there, and that includes a significant amount of the debris population at the current time. But as you can see, really it's increasing rapidly in current time. So this is becoming more of an issue of how we deal with this and how we treat the environment, and then how we're going to prevent these sort of catastrophic collisions. So the majority of these objects are located in the environment that we would call low Earth orbit. So this is altitude range maybe about 300 kilometers above the Earth to 1 or 2,000. There's kind of no strict definition of this, but roughly in that range. So this is looking at the distribution in altitude of the object. So on the bottom here is the altitude, and then the sort of height of the bar is how many objects, and then it's divided by type. And you can see the majority are around 400 or 500 kilometers altitude. That's where kind of the most commercial satellites are operating now. And really the reason that becomes the dominant place where most of these objects are is because it's a little bit you could think of as a bit of the sweet spot for operating. If you go too much below that altitude, the air becomes too dense, and your lifetime of the satellite isn't very long, so it's kind of going to come in quicker and you don't have much lifetime. If you go higher, there's a few things. One, it will be more expensive to get there, right? So you're going further from the Earth, so your rocket needs to be stronger, and so you're going to a higher altitude. And also if you're, say, looking at the Earth or transmitting any signal to the Earth, the further away you are, then you need more power or a bigger camera, things like that. So if you can be closer, it's better for most operations. So it turns out around 400 or 500 kilometers is a good place for a lot of operations to be. So that's kind of where it's a very congested environment in a sort of narrow altitude range. And just before we go into a bit more detail, it's worth talking about some of the different regions of the atmosphere, so that some of the terminology that I'll use later in the talk, it makes sense. So this is just looking at the temperature structure of the atmosphere, starting at the surface and going all the way up to space. So the troposphere here at the bottom is what we are, I think most people are familiar with, where we experience our day-to-day weather, and all of the weather is occurring. And then we have the stratosphere, and I think most people are probably familiar with this altitude range from the ozone hole. So that's, say, around 40, 50 kilometers above the surface of the Earth. And that's where the majority of ozone is. And then, so that's the stratosphere. And then way up a few hundred kilometers, that's where we have the thermosphere. And that's, again, this region where all of the satellites are mostly operating, this kind of bluish region in this figure. Co-located with that, I won't really discuss this in detail in this talk, but there's a charged part of the upper atmosphere, which we call the ionosphere. That also has a lot of space weather implications, and we also do a lot of work here to model that. But for most of this talk, you can just ignore that part. But understand that it's at the same altitude range, and it also has sort of importance for space weather, but not really a detailed focus here. So what is the danger? I kind of alluded to it a little bit, but if you have this very congested environment, one of the big concerns is a sort of destructive collision between two objects. And you might think, well, we have all this space, the satellites aren't that big, could they really run into each other? And it has happened in the past. So this is an example from over 15 years ago, where there was an actual collision between two satellites. So one communication satellite that was still active collided with a sort of no longer active satellite. And the concern when this happens is, you have two objects moving extremely fast, and so they'll collide and create a whole sort of cloud of debris. And so instead of having two objects, you create this sort of many more, potentially thousands of smaller pieces that then fill in the environment. So if you look here on the right, you can see in green is the kind of existing objects that were in space. And then after this collision, all of these red dots, those are the new debris particles created as a result of the collision. So instead of having two green dots, now we have all these red dots filling in the space. And so that creates sort of more population that you need to worry about. And we'll talk a little bit about, this can lead to more collisions again. There's sort of a cascade effect. And this is kind of extreme case of two satellites, but the danger is kind of always there. So because the objects are moving so fast, even a very tiny paint chip, this is an example from the space shuttle, where it was impacted by just a small paint chip that was 0.2 millimeters wide. And you can see the sort of debris, or the impact on the surface is this sort of cratering because of, these objects are moving about 7 kilometers per second or 17,000 miles per hour. So even a fleck of paint can create sort of catastrophic damage. So it's, we really need to pay attention to even the smallest of pieces. And if this hits a kind of critical component of a satellite, you can go from an active satellite to something that is no longer functional. So this is the other concern, that this is always a present danger, even from these sort of small debris. And this sort of ultimate danger of all of this that could happen is related to space sustainability and keeping the space environment usable for the future. So the kind of danger is that once you have one collision, you could lead to a chain reaction of kind of multiple collisions that would happen. And then you have two satellites collide, they create thousands of debris, and then that debris can hit another satellite, and then you hit another satellite, and so on and so on. And then you basically get this cloud of debris that's no longer usable. So this is looking at that kind of scenario, and could it happen using a statistical model where you look at, if you have a certain amount of new launches, so things going into space, a certain amount of decay, so how often you're deorbiting, and then a certain amount of collision, some probability of collision occurrence. And then over time, what would happen given some assumption on those factors. And in this scenario, there's other scenarios you could end up in. This is not guaranteed to happen by any means. But in this scenario, the orange is showing the debris that you would generate. And you can see that over time, there's kind of this significant increase in debris where it becomes a sort of exponential growth. And that is where you get to this situation where it's sort of a cascade effect and you no longer have a usable environment. And then the number of active satellites kind of goes to zero. So this is kind of one of the concerns with this sort of orbital debris and collision, and why we need to be able to predict why this is happening. And really the elements here for sustainability are two parts. One is a collision prevention, so you need to prevent objects from colliding. And then the other is kind of a balance between launching new objects into space and deorbiting old objects. That's more of a commercial and regulatory matter of the launch and deorbit and how you regulate those sorts of things. But the collision prevention is a bit more where the space weather and things like that come into play. So if we want to prevent collisions, really what that requires is knowing where you are and where you're going to be in the future. So the question is, if I'm starting a satellite that's initially at one point, so we have a satellite that is here initially, and then after some amount of time, where is it going to be in the future? That's essentially the question that you're asking to prevent two objects from colliding. Where is this object when it starts here? And where is it going to be? And is this other object that started here, when it's moving, are those two going to end up in the exact same space and hit each other? That's the question. So we need to be able to figure out, if I'm starting at this point, after some amount of time, where am I going to be in the future? And this future location, so if we want to predict where it will be in the future, this is based on, if you know the current position and the speed or velocity of the object, and then all the forces on it. And that's basically, then you can predict where this object will be in the future. So if we know all of those things, we can do this prediction, and we'll know where a satellite will be a day from now, for example. So we can relatively straightforward figure out where it is and how fast it's going. And then the question becomes, what are kind of all the forces that are acting on the satellite? And there are several different forces, so it's kind of shown here in a cartoon way. We obviously have gravity acting on the satellite. So we have Earth is a massive gravitational body, and the satellite is there, so it's being pulled by the Earth. And then we also have sort of other large gravitational bodies in the solar system can matter. For example, Jupiter can be a significant gravitational perturbation on a satellite. And then there's another sort of radiation pressure from the sun. So as the sun sort of hits the satellite, that has a small force on the satellite. And then there's also some sort of reflective pressure coming from the Earth. But the other force, which is kind of where space weather comes into play, is this sort of drag force that acts on the satellite. So even though we think of space as this sort of, often people think, oh, it's a vacuum, there's nothing there, so is there really any drag force on it? But it turns out there is enough density, even at a few hundred kilometers, that there is a drag force that's detectable, and that matters. So this drag force, we don't want to go into equations really, but the key thing you need to know is that it depends on the density. So, if an object is moving through space or the atmosphere, it depends on how dense that atmosphere is, right? Or you can think, as an example, if you're moving through a swimming pool, right? If you move your arm, it's very dense, the water, so it's harder to move. And so the drag force basically depends on the density of the fluid that you're moving through. So in air here, it's very easy. We can move our arms. Underwater, it's hard because the water is higher density. In space, it's much less dense than here, but there's still just a tiny bit of density. So that density still has a sort of drag force on a satellite. And so that is where this sort of space environment comes in to understanding this problem of predicting where a satellite will be at a future time, is how this sort of drag force acts on the satellite. So to do that, then we need to know this density, and that's the kind of key part, and that's where our research here comes into play, and trying to understand the density, why it varies, and how to predict it in the future. So this density, just very quickly, how does it look as you go into the space environment? On the left here is a figure just showing the density of the atmosphere as a function of height. And it only goes down to 50 kilometers, but it goes up into the space environment. And if you look at the sort of scale here, it's a kind of logarithmic scale, so it's exponentially smaller as you go to higher altitudes. So the density here is orders of magnitude smaller than what we experience on Earth, but it's still large enough that it actually matters, again, for the debris and how it sort of moves in its orbit. And the composition of the upper atmosphere also has a little bit of a role to play here. This second term here, this CD, is a coefficient of drag, and that depends somewhat on the interactions between the neutral gas and the surface. So if the surface is more oxygen or more nitrogen, it kind of impacts a little bit how this sort of drag force occurs. So we also need to know the sort of population of the environment. So this is the density, and how much does it vary over time, right? You might think, well, it's so small, is it actually changing enough to really matter? And so what I'm going to show here is a movie of the density of the atmosphere and how it varies at an altitude of 400 kilometers. So in this range where most of the satellites are operating, and this will be a 2-month movie, so you'll see it kind of just step forward in time every hour. And the way I am showing this is it's kind of divided by the average density, so you get a sense of the magnitude of the changes, if they're very big relative to the background or very small. So if it's in the middle here, around 1, that means it's the average. So it's basically the climatology. So you could think of this as, if you're talking about the temperature in March, normally it's 50 degrees here in Boulder. So that would be, 1 would be kind of 50. If it's 2, that means it's double. So next week when it's 80 degrees here in Boulder, that's a value of 2. When it's double this sort of average temperature. And if it's 0.5, that would be half the average. So that gives you a sense of the kind of scale that we're looking at here when you look at it. So why don't I go ahead and play the movie. And you'll see most of the time, it's kind of varying relatively small amounts. It's, you don't see there's some variation, but it's pretty small on this scale. It's not being twice as big. But you'll see as the movie goes on, there are times when it really gets very big. So it will exceed 2. There is one time when it goes up a little bit. And then there's another time, and then you'll see towards the end of the movie another sort of big jump as well. So here is, again, where it's kind of not much variation. And then here, coming up in a few days, you'll see this sort of big increase again. So there you see, again, this sort of, where it's twice as big as a sort of climatology. So there's these really big changes, and that can then impact the sort of drag that a satellite experiences. So where is all of this variability come from? That's the kind of key question, right? If we know it's there, but where is it coming from? So there's 3 main sources where this is kind of driven by. There's geomagnetic storms, which I think probably most people have at least heard of, peripherally in some way. There's solar irradiance, which is basically the energy from the sun in sort of not in a sort of geomagnetic storm, just kind of it's always there. And then there's kind of terrestrial weather effects, where sort of weather events on the lower altitudes propagate all the way up into the space environment and then can impact the space environment. So I will go into each of these in a little bit more detail and give you some examples of how it impacts the density that we see in the space environment. So first, geomagnetic storms. I think this is probably what most people are familiar about when they think of space weather and how it impacts the space environment. So these kind of start at the sun, and they're due to sort of eruptions on the sun, so-called coronal mass ejections. And here on the right is a sort of animation of one of these where you see this sort of explosion coming off of the sun, and that is sort of directed towards Earth and then can impact our sort of magnetosphere. And the magnetosphere is this sort of protective, some people would call like a bubble or shield of Earth, which is formed from the Earth's magnetic field, and that sort of helps prevent these sort of charged particles from the sun coming directly into our atmosphere, and it sort of causes the particles, funnels them into the high latitudes where you get the aurora, because these sort of solar particles are coming in to the atmosphere. So now I'll play a movie. This is actually from a model developed here at NCAR in collaboration with NASA, and they made a pretty animation of this. And you'll see here this sort of interaction of a coronal mass ejection with the magnetosphere. And I just want you to see how sort of dynamic all of this is. So it's not just like it happens once. You see there's all of these sort of small scale features, and it's kind of always sort of varying. And so you can see these sort of, when the storm hits, you see a sort of pulse, and then there's all these sort of smaller variations occurring as well. And so these sort of interactions with the magnetosphere, then that energy gets put into the Earth's upper atmosphere, and then that causes sort of changes to the density. And this also is what drives things like aurora that people are more familiar with. So how does these sort of storms impact the density? I'm going to play this sort of short time period of this movie again. And this is when one of these very large geomagnetic storms hits. And so this is when you can see this sort of increase in the density goes up to a factor of 2 over the average. And you'll see here, you get this sort of huge increase in the density of the upper atmosphere. And that occurs during one of these very strong geomagnetic storms. You might remember this was in May 2024. You might remember here in Boulder, you could see aurora if you remember that. So that was this event, and that's how much the upper atmosphere was changing at the same time. And so these storms, how do they really impact these operations of satellites? this is looking at basically during a geomagnetic storm, how many satellites are changing what they're doing. So when the storm occurs, do the satellites kind of have to maneuver in their orbit to stay either safe or stay in the sort of orbit that they want to be in? So what you see here is over time, this is looking at this same sort of geomagnetic storm that occurred in May. And then this blue line is just giving a measure of how strong the storm was. So you see it gets very strong. And then the black line is the number of satellites that had to maneuver in space. So you can see right after the geomagnetic storm occurred, something on the order of 4,000 or 5,000 satellites had to do some maneuvering in space. This can either be to avoid a collision, or if they want to stay in a certain kind of altitude, if the environment gets more dense, they're sort of brought down, so then they maybe need to boost their altitude up or try to stay in the exact space that they want to be in. So these sort of increase in density really does have significant impact then on the satellite operations and how they have to deal with this to maintain their orbit and how they want to operate. The other main source of variability is solar irradiance. So I think everyone is familiar, the sun gives off energy, and we're all familiar with kind of visible sunlight. And in our everyday life, we're familiar with the visible sunlight that reaches down to the surface. But really, the sun gives off a whole spectrum of energy in different wavelengths. So the visible is kind of one part of the spectrum of energy given off of the sun. But there's other, both shorter wavelength and longer wavelength energy as well. And it reaches into different parts of the atmosphere. So the visible kind of comes down all the way to the surface. But the other wavelengths of light, like the ultraviolet, that is, there's a narrow portion that can reach the surface, but most of it is absorbed by ozone in the stratosphere. So we're not really concerned about most of the ultraviolet radiation at the surface. And then there's other parts of the spectrum that are absorbed at much higher altitudes in the space environment. So especially the extreme ultraviolet and ultraviolet, these are what primarily drive this sort of heating and of the space environment. So it's not really the visible spectrum, but it's these other portions of the spectrum of energy given from the sun. And why it kind of matters is that the sun has this sort of solar cycle where it goes through every 11 years. It has a sort of maximum and minimum. And if you look at the sun in a sort of ultraviolet wavelength, this is what the sun would look like. So in solar minimum, here at the top, and then it kind of goes around this way to a solar maximum and then back to a solar minimum. You can see in solar minimum, the sun is very sort of dim in these wavelengths in the ultraviolet. And then in solar maximum, it gets very bright. And on Earth, we don't really consider this sort of, or the surface, we don't really think of this solar cycle in the visible spectrum because it doesn't really occur to the same degree. But in these sort of ultraviolet and the parts of this spectrum that impact the upper atmosphere, it really matters and is quite big. And one way you can measure that is with this so-called sunspot number. This is not the best way by any means of measuring it. It has some deficiencies, but if you look, it has this sort of regular up and down cycle that we have. And so this is looking back over 100 years of the number of sunspots that occur on the sun, and you see this sort of oscillation that occurs roughly every 11 years, and then at the end you can do some prediction of how it will evolve in the future. And so there's this sort of regularity to this, but also some differences from each to the next. So it's not a strictly repeating cycle. So if you want to know what will happen in the next cycle, you need some prediction. And then this sort of cyclical variation in the sun really has impact on this space environment. So here is looking at the density changes over time that you see in observations going back to the 1970s of the density of the upper atmosphere at 550 kilometers. So you can see, if you look at the blue line, which is a yearly average, you can see this sort of cyclical behavior, which is driven by this solar cycle. And the key point here, you can see, if you look at the scale, this is in order of 100 times difference from the solar minimum to solar maximum. So it's really not a minor change, this impact of the solar cycle and the long-term changes in the sun. They really have a very big impact on the amount of density in the upper atmosphere. And you can also notice, I will talk about this a little bit more, there's kind of this gradual trending down over time, which is partly driven from increases in CO2, but also a little bit due to a weakening of the solar cycle. So how do these kind of long-term changes impact the sort of satellite operations and understanding the environment? The main thing, or one key thing, is predicting the future lifetime of a satellite. So because satellites are often up for, they could be up for 10, 20 years, if you have a very high and dense atmosphere, that means it's not going to last as long. If it's sort of lower density, then it will stay in orbit for a longer time period. So what you're looking at here is a sort of future prediction of how long two satellites will stay in orbit. So one, the initial position kind of starts around 430 kilometers altitude, and the other starts higher. And then they basically run scenario of different levels of solar activity, how long and how quickly the orbit is going to decay. So if you have we'll focus just on the red line here on the bottom. If you have some kind of a lower solar activity scenario in the future, it's basically going to decay at this slower rate. And so the satellite lifetime will be much longer. If you have a medium level of solar activity, it will decay much faster and potentially re-enter years earlier. And if it's a very high solar activity, it might re-enter very quickly. So for mission planning and the lifetime of a satellite, it really matters to be able to predict what the sun is going to do over multiple years, and then how that impacts the space environment, so that satellite operators can plan and use their fuel appropriately. Because if, for example, if you want to last for a longer time period, you might raise your orbit earlier to a higher altitude so you can last longer. But if the solar activity is going to be low, then you could just stay in a lower orbit and not necessarily use the fuel, which is very, a precious resource. And then the third area where we see impacts, I will stop the movie first, where we see impacts on the space environment is terrestrial weather. So what I'm going to show here is a movie of the model simulation looking at a volcanic eruption that occurred in the Pacific underwater, and then how that impacted the space environment. So you'll see on the bottom the perturbations in the surface pressure from this volcanic eruption. And then here you'll see the change that occurred in the ionosphere. So this is no longer the sort of neutral density, but I think it illustrates this sort of coupling. And what you'll see happens is you get a sort of eruption in the surface, and that creates waves in the atmosphere. And then these propagate all the way up to a few hundred kilometers. So even though this is occurring at the surface, these waves can propagate all the way. And then you'll see these sort of effects kind of rippling out at a higher altitude. I'll go back to the beginning. So here you see this eruption, and then these waves in this surface pressure going out. And then you see all these kind of ripples occurring in the upper atmosphere that are sort of spreading out. And you'll actually see these kind of go all the way around the surface of the Earth. And then they kind of wrap around. So this is one example of a sort of impact of terrestrial weather on the space environment. But how does this impact space debris or the satellite environment? What is shown here is looking at the error in a predicted orbit. So if you're at one point and a day later, where a satellite will be after one day, and how far that error is if you completely ignore the effects of terrestrial weather. So if you have a model of the density that ignores those effects, how much error would you get in the position after one day? The left here is at an altitude of 200 kilometers, and you can see you would get a difference in the position of the satellite of something 10 or 15 kilometers. So 6 to 10 miles difference in where a satellite is by neglecting the effects of terrestrial weather at an altitude of 200 kilometers. If you look at a higher altitude, say 400 kilometers, Now the difference turns out to be much smaller. So this is on the meter scale now. So these terrestrial weather effects mostly impact the lower part of the thermosphere, and the higher altitudes are more impacted by this sort of solar influence. But by impacting the lower part of the sort of thermosphere, that means it really has an impact on re-entry of objects. So one of the things as an object is sort of reaching its end of life, it always will re-enter the atmosphere. And you want to be able to predict where that is going to occur. Ideally, you try to re-enter it into the ocean or something like that, not over a major city, ideally, right? So you go into the ocean, and so you want to be able to predict where that will occur. And so we did an experiment using our models, looking at two scenarios. One in this orange line, if you have so we start an object at 200 kilometers, and then we run it through a simulation of how long it will stay in orbit until it re-enters. And so we look at how long it will take. And the orange line is if we only consider effects from the sun. And the blue line is if we consider both the solar effects and also these sort of terrestrial effects coming up. And you can see for the most part, they're showing similar variation. So they're kind of controlled by the sun. But if you look here, there are some differences, significant differences between these two. And you might say, well, okay, the difference is a tenth of a day in the amount of time. But a tenth of a day is almost an entire orbit. So over that amount of time, you basically go from one side of the Earth to the other. So that is a level that really matters. So to be able to reliably predict reentry, you also need to account for these sort of terrestrial effects as well. And the last part of the sort of terrestrial effect is this sort of effect of carbon dioxide and how that has impacts on the space environment. So what you're looking at here is a profile and how much the neutral density changes from the 1970s to 2000s from a model simulation. And you can see the density change in the atmosphere from 1970 to early 2000s was about 10%. So there was a 10% reduction in the density at this sort of altitude where most satellites are operating from 1970 to 2000. And this is mostly due to carbon dioxide. We always think of it as sort of a heating gas in the surface, right? But in the space environment, it actually acts as a cooler. So it sort of cools the space environment, and that leads to this density reduction. And this is from a simulation, but this is verified by observations. So here is looking at the kind of density trend that you get from real observations. And you can see it's about 3% per decade. And this is 3 decades, about 10%. So they match quite well. So this is another effect where the sort of terrestrial environment or what is happening near the surface then impacts the space environment. So how do we kind of predict what is happening? I've explained to you why we need to predict the densities, but how do we actually do it? One way you can do it is to build a model. And this is in many ways quite similar to how you would build a weather model. So here is, at a very high level, how you would build a model of the atmosphere. And not for space weather specifically, but just for, say, if you want to predict the weather and how it's going to happen. You essentially divide the Earth up into grid cells. So we divide, every few hundred kilometers, we create a box, and then we do the same in height. And then we, divide it up, and then we use equations of motion, and then we have the atmosphere, and then we include additional physical processes. This would be for an atmosphere environment where you would have things like convection, how it interacts with the ocean and land, things like that. But if we do it for the space environment, it turns out to not be exactly the same. We don't just take a weather model and then add a lot of layers till it reaches the space, and then we just use the same thing. We have to include a lot of additional physical processes. So this is kind of a very cartoonish way of looking at how we do this for a space environment model. So we still have this sort of terrestrial environment that we build it off of, and then the Earth has this magnetic field, and we need to account for that. So we add in the sort of effects of the magnetic field and how that interacts. We include additional chemical processes for the upper atmosphere. And then, of course, we have the effects of the sun. So we kind of, when we're trying to build a model for the space environment to predict these density changes, we take something similar to a weather model, but then we kind of make it in a way that is designed for the space environment by adding additional processes that are needed for those altitudes. And there's really a rich kind of history of doing this here at NCAR, and this has been done for over 50 years here in sort of various fashions, of course, improving over time. So here is going through kind of the history of the development. It really started in the 1970s. So over 50 years ago, there was a kind of 2D model developed of the thermosphere. So it just had kind of one slice and then went up in altitude. So a very kind of basic model, but it was targeted really for the space environment, for understanding those altitudes. And then a few years later, there was a 3D model of the thermosphere. So from about 100 to 500 kilometers, there was a model developed. And then this we call the Thermosphere General Circulation Model, or TGCM. This kind of progressed over the next few decades, and there was an I added. So the I is the ionosphere part. So we went from just a kind of neutral model, then the ionosphere, this sort of charged part. And then an E was added years later, and that's the electrodynamics, this sort of interaction with the magnetic field. And then later, around late 90s, 2000s, the effects of these sort of terrestrial weather environment was more noticed. So this model was extended downward to lower altitudes, and then at the same time, a model was developed starting at the surface and going up to the lower part of the space environment. And then early 2000s, another model was built of this sort of coupled magnetosphere system, so to really better account for the forcing from the magnetosphere and this external forcing. And then later in, say, 2010s, we had this sort of full whole atmosphere model, we call it, that extends from the surface up to the space environment, or space. And then the last, latest development is this magnetosphere model, which is kind of a next generation of this model that was developed here. And I should say these times are kind of initial release, so a lot of them have been kind of developed through the decades. For example, this model, the third version was just released a few years ago, so it's still actively being developed. And I'll go into a few of these in a little bit of detail. So one of them is this sort of what we call WACM-X that we develop here, and this is built off of the community Earth system model, which is developed here at NCAR. And what we do is we basically extend that atmospheric model up into the space environment. So we took the sort of basis of this model, which is geared towards Earth system prediction, and then extend it all the way in altitude and add all of these extra physical processes. And this is really targeted towards understanding these terrestrial effects on the space environment. And then I will not go into this in any detail. I will just give you the viewpoint that it's complicated. The other latest model development is this so-called MAGE, or multi-scale atmosphere geospace model. And this is really bringing together a number of different models, and it's targeted towards getting this sort of external forcing. And this is a partnership between NCAR and Johns Hopkins APL through a NASA-funded center. And you can see this gets quite complicated quite quickly, but this is one of the sort of latest developments. And then the last thing I want to talk about is how we kind of improve predictions once we build all these models, and then models are not always perfect. As much as we work on them and we want them to be very good, they tend to still have some problems. So one of the things we can do is bring in observational information. So all kind of weather prediction models function this way. You have a model that forms the background of it, and then you have some observation of the environment, and then you try to kind of bring those two together to correct your model. And so we do the same thing with our space weather models. And this is a kind of very high-level view of what we would call data assimilation. And what it does is, again, like I said, we take the observations, And we have some statistical algorithm where we combine those observation information with a model prediction. And then that gives us a better state of the atmosphere or space environment. And so that is what we work on as well for the space weather. And this is basically how all, until kind of a year or two ago, all weather forecasts you would ever see are built off of this methodology. Of course, now sort of AI weather forecasting is more of a thing, but this is the way you would do it. And then you take this sort of state, and that gives you your next prediction. So you have a better kind of understanding of what is going on. And it turns out that just like modeling the space environment, this is also not as, we can't just take a method that was designed for predicting the weather and apply it, blindly to the space environment and not fix it. So there are some key differences between kind of doing terrestrial weather prediction and predicting the space environment. One of them is, as I mentioned, this space environment is kind of a bit of a forced system because it has these sort of external drivers. So you can think of this as the space environment, you end up, if you're starting in two different places, you'll always, because it's forced, you tend towards the same final spot. And one way you can think of a force system, say you have your oven at home. You set the temperature to 300 degrees and hit start. Eventually, that oven will get to 300 degrees. It doesn't matter if it started at 50 degrees or 30 degrees or 70 degrees. You're forcing it towards the same spot. And over time, it will get there. That is kind of how the space environment acts. It's kind of depends somewhat on the initial state, how long it takes to heat up, but ultimately it will end up in the same spot. And weather prediction in the sort of traditional sense for, we think of it, is more of a chaotic system. You've probably heard of this, so-called butterfly effect where, some butterfly flaps its wings and then it creates a tornado or something halfway around the world. And that's how we think of terrestrial weather prediction. It's more of a problem of initial conditions than forcing. So it's a slightly different method that we have to apply for doing data assimilation and sort of bringing in observations in the space weather environment. So we've developed these methods, and we can show how they work for improving density predictions and how well we can predict the density. So here is an example. This is for one geomagnetic storm. So here the black line is an observation that we have. This is not the observation that we're bringing in directly. It's kind of independent. And you see during the geomagnetic storm, you get this huge increase in the density, and then it decays over time. And so what we did was we brought in, using one of our models and data assimilation systems, an observation that is kind of targeted at getting this decrease and how well it decreases. This is only from one set of observations, so it's not as good as we could really do. The blue line here is if we run our model without bringing in any of these observations. So you can see it, it gets this sort of increase and then this decrease, but it could do better for sure. And then the magenta or purple line is when we bring in these sort of observations. Again, this observation specifically is targeted toward this kind of decaying phase. And you see it kind of better captures, and this line is much closer to the black line. So we can improve our sort of density, how well we can constrain it. And the green line here is if you just start a forecast here. So even our forecast is better for several days in this case. So we can really improve through these sorts of methods. And then once we get this, you can see this forecast is better, but it's still not as good as it could be. So one of the things we can then apply is sort of a post-processing. So we've been recently doing some work with other collaborators at NCAR that are more focused on terrestrial weather, but we take their techniques for post-processing and apply it to a space weather forecast. This is an example. It's not really the density problem. It's, again, looking at the ionosphere, but it shows how well we can kind of correct after the fact a forecast. So we have the red line here, which is our model forecast, and these black dots are what the observations are. And you can just look very clearly, at times like this, the The red line does not match the black. So we're quite far off in our prediction of what is really occurring. But these grayish black line here is a corrected forecast where we take a lot of our forecasts and we look for a sort of analog to that forecast so we can try to get a better sort of corrected prediction. And then you see this black or grayish line very closely match the observations. So we can really, through these post-processing techniques that we're developing, get a much better prediction. So with that, I just want to give you the kind of key points again, and hopefully you're convinced that the space environment is important for satellite operations and that we really need to be able to predict it better so that we can do things like better predict the satellite orbits and prevent these sort of collisions that could occur. And this is really due to three factors. There's the sort of geomagnetic storms, solar irradiance or solar forcing, and then also the terrestrial weather. And then, to do this well, we need both to forecast the drivers. So there's also work, going on here at NCAR to forecast the drivers and predict what's happening at the sun, and then also how it really impacts the environment. And then we're doing work to really improve the modeling so that we can get better forecasts for the space environment. So for that, I will stop and thank you for coming, and I'd be happy to take any questions. Thanks.
All right. Thank you so much for that presentation. And I can get us rolling with a burning question I have from one of your earlier slides about UV light being more intense during solar maximum. Should we be wearing more sunscreen during solar maximum?
Not that I know of. Most of the UV is absorbed before it reaches the surface. So it's really a small spectrum that really can actually reach the surface. So as far as I know, we don't need more sunscreen during solar maximum.
All right.
But I could be wrong. Maybe someone can correct me.
Yes, in your opinion, yes. All right, yes, let's go. Oh, let me come bring the microphone to, all right, for our online audience so that they can hear you as well.
Thank you for the presentation. I wanted to ask who's responsible for creating the space forecast? Like, for instance, Hawaii's volcano just started erupting yesterday or last night. So that obviously impacts whatever forecast today and, until it stops. Is NCAR creating or producing those on a daily or hourly basis, or does some other entity do that?
Yeah, very good question. And I apologize, I should have maybe discussed the sort of operational side a bit more. So really the agency in charge of the space weather predictions is NOAA. So down the hill on Broadway, that NOAA office, there's the so-called Space Weather Prediction Center, and they're in charge of the space weather predictions. What we do here is really more targeted towards research and then informing better ways to build models, do things like data assimilation, and then hopefully transition what we develop to what NOAA is doing in their operational forecasting.
And so just to follow on, do we know the impact of that division with respect to the budget cuts that have happened with NOAA? Like, are they still able to do that, or have they had tremendous cuts and so those reports aren't coming out?
Yeah, I can't speak fully to any effects that they've had. I know they're certainly still providing operational forecasts, but the full extent that they may have been impacted, I really don't know.
How close are we to in the modeling, in the accuracy of models over time, getting better and better? How close are we to getting to the place where we can actually take two bodies in orbit and say, oh, we've got a imminent collision coming up in in the next month or something between these two objects? Yeah,
so a month would be, realistically, people are not even looking a month. They're really looking, say, a few days in advance. There is, there is understanding of if two objects might collide. really where the issue is currently is you can think of it as a probability problem. So you have two objects, they may or may not hit, and there's uncertainty on where they will be. Say if tomorrow an object's here, will it be here or some range around here? And so that range right now is very big because the models are not that good. So if you can improve the models better, then you basically shrink that sort of uncertainty to a narrower region. So now you could think, well, two objects, maybe they will collide because they have this big uncertainty. So their sort of error or uncertainty, those uncertainties might overlap. So depending on how much risk someone might want to take, they would say, well, there's some chance, maybe small, few percent, that will collide, but we don't know because our ability to predict it is so uncertain. But if you can make the prediction better, say you have better knowledge of the density, then you could shrink that uncertainty smaller, and then you have more confidence of, well, we're really not going to hit. We'll come close. We can wave to each other or something, but we're not going to hit each other. And so that is where the sort of modeling can help.
Thank you. Follow-up to that question is really the whole process of modeling and prediction is focused, I would assume, just on active satellites. Like there's not much we can do about inactive satellites or other space debris in terms of imminent collision. I would assume it's only in active satellites that we could have actually some ability to move the orbit of that object if somebody deems it necessary.
Yeah, of course, you can have an active satellite and an inactive satellite collide. So you need to know where the inactive are. There is certainly, it's a whole nother area of research and people trying to figure out ways to deorbit debris and things like that. And that is, a concern of if you have too much stuff that is no longer active, could you come up with a way to basically deorbit it or come up with those things? But I don't think it's an easy engineering problem. From my understanding, it's quite hard.
All right, we have an online question, so we will pull that up on the screen. This question is from Jenna. So the question is, who or what organizations monitor where satellites and space debris are?
So it's mostly done, historically in the US, it is done by the Air Force, and they have in Colorado Springs the so-called Space Command, and they're in charge of tracking everything. I think in more recent years, there's private companies and things like that are getting more involved in doing that. But historically, it's been a sort of government service, and they sort of track and release a catalog of everything that is tracked. But that is the other, I briefly mentioned it, we can really only track, bigger objects. So there's a lot of small stuff that we can't track, and there's, active, not here, but active work in trying to, be able to track smaller objects.
Hi, thank you. I have a question on the slide that you showed, long-term variations in density impact satellite lifetime.
This one, I think.
Yeah, okay. It's not showing, but I have a copy of it here. So wouldn't you expect for the high-altitude satellite at high solar activity and for the low-altitude satellite at high solar activity, when the high-altitude satellite at high satellite activity gets to 425 kilometers, that its slope and decay should match that as the one that started at the lower orbit? Or is the high, medium, and low activity just modulating historical space activity, and that would explain?
So it's kind of looking at a variation over time. So it's not a kind of constant high activity. It's looking at if you had either a higher solar cycle or a weaker solar cycle.
It includes the solar cycle.
Yeah, exactly. Yeah. So if you had either very strong, how long you would last, or kind of lower, and then how that would impact how quickly.
All right, another question in the room.
So I'm interested in your carbon dioxide effect. I've been navigating OCO2 since 2014. So if you take out the solar cycle effect and maybe look at minimum around 2018 or 2019, so 11 years later, if you extrapolate your graph a little bit, the density must have gone down by at least 10%. I'm not sure if it curves back around and at all, but say it's 10 or 20%. So if I compared the amount of fuel in our drag makeup maneuvers, we should see a decrease between those two eras, and that'd be interesting.
Yeah.
In fact,
Yeah,
I'll send you the data.
Yeah, it would be interesting to see how much that impacts how much fuel you need. Of course, it's complicated because the solar minimum are all a little bit different. So how much you get, how minimum it really is, kind of matters as well.
All right, another question in the room.
Thank you for your presentation. Is there a process in place when you want to put a satellite in orbit? Because at the beginning slide, you had amateurs and commercial.
Oh, yeah. So the amateur on that side is actually academic institutions. Why they consider them amateur, I don't know. but if you actually look at the details, they academic institutions, that's what they classified them in that report, was amateurs. So yeah, you can interpret that statement however you want. So I'm not an expert in that, but there is a regulatory process, and if you're transmitting at certain frequencies, you need a license, and there is a process. So amateur is maybe not someone in their backyard. It's academic institution. Yeah.
All right, another question from Jenna. Will it ever be possible to clean up space debris?
Yeah, this is kind of the question the gentleman here asked earlier of, is there a methodology where you could, grab onto something and bring it down, or somehow force it gravitationally to deorbit? And that's certainly something people are interested in working on. I don't really know enough of the details on that. It's more of an engineering problem, I think, but certainly people are trying to come up with solutions.
Hi. Sorry, we spoke a lot about LEO, but does space weather affect the different orbits differently?
Yeah, so it does in different ways. Really, the density kind of decays exponentially. So once you get high enough up, this sort of drag force no longer becomes the dominant or a factor in sort of orbit propagation. So in that way, it's less important. But there's other space weather effects that you might experience at a higher altitude. Say, you're less protected from particles coming in. So you can have a very high energy particle from the sun, could impact electronics or things like that. And the radiation effect from, is more of a factor at those altitudes. So there's other space weather effects, not the same, but they're not, immune to effects of space weather.
I love watching the International Space Station, and I have an app that tracks it. Is it impacted with all of this?
Yeah, certainly. You hear every once in a while on the news that they have to adjust their orbit because they might collide with something. And this comes into the earlier question, that uncertainty, and of course the risk that they're willing to take is very, they have to be very careful. So if there's any chance they might collide with something, they will move. And same, of course, the solar cycle they have to deal with. When it gets more dense, they probably have to raise their orbit up. So certainly they're affected a lot. And they're just as sort of, I didn't mention it, but they orbit around 400 kilometers. So they're right in that sort of range where a lot of other stuff is.
Yes, go ahead.
Testing. Nick, I have a two-part question. One, I'm curious kind of on how you got interested in this line of work and space weather in general. And then what do you see kind of like looking forward where the field is going, like pressing questions that you and your team are grappling with?
Yeah, so how I got into it, I guess like most people. So I actually have my degree is in aerospace engineering. So I kind of came at it from space engineering, and then I went to CU for my graduate degree, and a lot of the sort of research in the aerospace department here is focused on space environment, and it's an interesting problem as well. And then where things are going, the sort of way people often refer to it is space weather prediction is I don't know, some number of decades behind kind of terrestrial weather prediction. So you could pick 2, 3, 4, I don't know how far back you want to go. But so really, working to advance how well we can predict it, and bringing in observations much more that has historically not been done as much. These sort of combining the observation with the model so we can get better prediction.
Thank you. What type of observations are you bringing into the models?
So
Sensors.
Yeah, so there's a lot of, well, I shouldn't say a lot. There's not that many, actually. That is one of the additional challenges. There's really not that many observations of the space environment. So there tend to be kind of research-type sensors that are built by the experts at the university, not the amateurs. The experts build them, and they could be remote sensing or things like that. Another, you can go out in the hall. There's a beautiful so-called cosmic satellite hanging from the ceiling. That is one of the observations that we use as well.
All right, well, let's have another round of applause for Dr. Nick Pedatella. Thank you all again for attending this lecture on space weather as a part of our Explorer series. We still have several more events coming in March and April. So on March 27th, this will be a virtual conversation about the applications of artificial intelligence in Earth system science from 11 a.m. to 12 p.m. Mountain Time. On April 8th, we will have Integrating Expertise, Predicting Hazardous Weather Through Convergent Science and Artificial Intelligence here at the Mesa Lab from 7 to 8:30 p.m. Mountain Time. On April 14th, we will have a virtual discussion about sub-seasonal weather prediction using explainable AI. And on March 28th, we will have an event up at the Loveland Museum from 1 to 2:30 p.m. Mountain Time titled Inside NSF NCAR Science, Stories, and Breakthroughs, where we will talk a little bit about some of the work that we've done in the past and how we're doing similar work or how that work has evolved to current day. So if you are interested in more of these Explorer Series events or any other events, please check out our website and be sure to sign up for our newsletter at the front desk. We hope to see you all next time, and have a great rest of your evening.